Hello everyone, I am Ikojo Simon, a second-year PhD candidate at the Australian National University. I am delighted to welcome you to the presentation of our registered report titled Automated Detection of Algorithm Depth in Deep Learning Frameworks, an Empirical Study. This research is collaboratively done with my supervisors, Shiraz Hezraki, Alex Potanin, and Oswamanen, all from the Australian National University, and Fatima Fard from the University of British Columbia. We want to thank the organizers for giving us the opportunity to present remotely. Technical debt is a metaphor that reflects the long-term costs of the suboptimal choices made during software development, which might have short-term benefits but result in increased maintenance costs. Algorithm debt is a new type of technical debt resulting from the suboptimal implementation of algorithm or logic, which can negatively impact system performance as the system evolves. There are different types of technical debt such as code, design, test, and architectural, which are prevalent in general software systems. Algorithm debt is a type of technical debt recently uncovered in deep learning frameworks. Technical debt in general is caused but not limited to poorly written code and insufficient testing. Algorithm debt in deep learning is caused due to the complexity of deep learning algorithms. In addition to increased maintenance costs, algorithm debt can lead to poor scalability of models and model degradation. Automatically detecting algorithm debt in deep learning frameworks is important for early identification, reducing future re-engineering of the code base, and also improving model scalability. Previous studies on technical debt show that machine learning and deep learning models can help in automatically detecting technical debt from source code comments known as self-admitted technical debt. However, self-admitted technical debt in machine learning and deep learning systems are different. This is partly due to their added learning components and unique development pipelines. An example of self-admitted technical debt, specifically algorithm debt from an open source code, is shown on the screen, where the developer is explicitly asking if there is a faster way to do pooling in the channel first case to optimize the algorithm that has been implemented. Our goal is to empirically investigate the performance of various machine learning and deep learning models in detecting algorithm depth in deep learning frameworks. And to address our goal, we have two research questions. One, which feature extraction methods enhance the performance of machine learning and deep learning models in detecting algorithm depth? And the second is, how do different machine learning and deep learning models perform in detecting algorithm depth? To answer our research questions, we will use the dataset curated by Liu. We selected this dataset because this was the dataset that was used to uncover algorithm depth in deep learning frameworks. The authors extracted comments from 7 deep learning frameworks hosted on GitHub, which are TensorFlow, Keras, Deep Learning for Java, Caffe, PyTorch, MXNet, and CNTK. The authors manually classified self-admitted technical debt in these frameworks into one of algorithm, compatibility, defect, design, documentation, requirements, and test depth. The dataset consists of over 300,000 comments, with algorithm depth having a total of about 6 to 21% across these frameworks. We will perform empirical studies using different approaches: TF-IDF, count vectorizer, hash vectorizer. We will use embeddings from models founded in deep learning such as Robera, Albert, and large language models such as Instructor and Voyage AI. We will enrich the dataset by incorporating algorithm depth related words to train various machine learning and deep learning classifiers, which are the support vector machine, logistic regression, random forest, Robera, and Albert. We considered several threats to the validity of our work. To mitigate potential researcher bias from the manual classification process, we will use an already labeled dataset. We will use stratified 10-fold cross validation to reduce bias and variance to the test set. We will use metrics such as precision recall, F1 score, and macro averaged F1 score, consistent with previous studies. Please feel free to contact us if you have any question. You can download the complete report using the link on the screen, and we also invite you to scan the QR code to complete a questionnaire on algorithm depth. Thank you for your time.